My name is Nicola Houtman. I'm an MSc student at UVic in the Spectral Lab, and I'm going to be presenting on my development of a methodology to map forage fish with drones in nearshore ecosystems. My research question looks specifically at the environmental conditions that are optimal for data collection. Forage fish is an ecological role that refers to organisms that eat zooplankton and are eaten by piscivorous fish, mammals, and birds, and this role is usually filled by a few species that exist in great abundance. In BC, there's a lack of spatial data on forage fish, and the most ecologically important forage fish are thought to be Pacific herring, Pacific sandlance, and northern anchovy. Most methods for monitoring forage fish that currently exist cannot access important shallow nearshore habitats, and if they can, they're usually resource intensive or can only cover small areas. Drones offer an efficient, non-invasive method that can quickly cover large areas of shallow nearshore habitats. However, the imagery quality collected by drones is highly subject to a suite of environmental variables that affect the ability of the drone to see through the ocean surface and into the water column. So here we can see this herring school, and the school is quite obvious, but these are optimal conditions, and as conditions worsen, fish schools get much harder to see in drone imagery. In order to identify what environmental conditions are ideal for mapping forage fish in, I designed an experiment where we took videos of a model fish school at 4 depths in a wide range of conditions. The lures were chosen to represent forage fish seen in test surveys, where we saw dark fish over light bottoms, represented by this dark fish on the top left, and fish flashes as fish turned on their side and reflected light into the sensor. For every sample, I recorded these environmental variables: sun altitude, sea state, wind speed, cloud cover, turbidity, and tidal height. For each sample, I looked at the video and counted all the fish lures visible at each depth. So this example was taken in optimal conditions, and you can see that the dark lures are quite visible at 0.5 meter, but they start to disappear at about 1.5 meters, and the silver lures are much more visible, but the smallest silver lures start to disappear at about 2 meters depth. The analysis of this fish lure count data consisted of a cluster analysis followed by a principal components analysis and a Pearson's regression. So the cluster analysis grouped the environmental conditions sampled into 5 clusters that I then compared to the lure counts, and then I completed a PCA and a Pearson's to determine how much each environmental variable mattered to the lure visibility at each depth. The analysis found some interesting patterns that differed for the dark lures and the 3 silver lures. So the dark lure was much less visible than the 3 silver lures and was most affected by cloud cover. So clouds scatter sunlight before it can reach the surface and illuminate subsurface features, and mixed cloud conditions can cause irregular patterns of light and cloud reflectance on the surface. So it makes sense that clear conditions with the most light available create the best conditions for seeing this dark lure. The silver lure visibility decreased with smaller lure size and was most impacted by rough conditions, followed by the angle of the sun. So this is likely because high sun angles cause glint on the water's surface, and when there are waves, which can be caused by wind, the sunlight, even at lower angles, can cause irregular patterns of glint on the surface and can even mimic forage fish flashes, making these silver lures harder to see.